Hello students, welcome to another session of topological space. Okay, here we are discussing continuity in topological space. Yes, we have a theorem. Composition of continuous functions are continuous. So in the last class we have discussed the property of continuous functions and basic definition of continuous functions, etc. So how can you prove this? To prove this theorem, we use the criteria a function is continuous if and only if its inverse image of open set is open. Okay. So, suppose we have a topological space x to 1 and y to 2, z to 3. Okay. And f is a mapping from x to y, g is a mapping from y to z. And without loss of generality, we can assume that f is on 2. Okay. Then, suppose f and g are continuous, we need to prove that its composition, either f composition g or g composition f. Here g composition f from x to z is continuous. So we have to prove that g composition f is continuous. So for the proof, let f from x to y be continuous and g from y to z be continuous. Claim g composition f is continuous. And see, g composition f is a mapping from x to z. To prove inverse image of open set is open, we have to consider one open set in z with respect to tau 3, and we want to prove that g composition f inverse of that open set will be open in x. So let V be an open set. V be an open set in Z. That means V belongs to tau 3. Since V belongs to tau 3, then since G is continuous, inverse image of every open set in Z will be open in Y. So G inverse of V will be here. G inverse of V will be open in Y. Okay. Since let V be an open set in Z, then G inverse of V is open in Y, since G is continuous. Okay. Okay, now consider G inverse of V. G inverse of V, you take U equal to G inverse of, let U equal to G inverse of V. Then U is an open set in Y. Also, F is continuous mapping. Therefore, inverse image of every open set in every open set in Y will be open in capital X. So, if we take U equal to G inverse of V, then F inverse of U is open in capital X, since F is continuous. Therefore, F inverse of U is nothing but G inverse of V. So, F inverse of G inverse of V is open in X. What is F inverse G inverse of V? It is G composition F whole inverse of V is open in X. So, what you get now? If V is an open set in Z, then G composition F inverse, is a mapping from X to Z. So, V corresponding inverse G composition F inverse of V will be here, which is open in capital X. Therefore, by again criteria of continuity, G composition F is continuous. So, composition of two continuous function is always continuous in topological space also. Now, for another case, example, or for a result, let x to and some z comma u be topological spaces. Okay. F is a mapping from x to z, and y is a subset of capital X. Okay. Then, if f is continuous, okay, then you consider the mapping f restricted to y, okay, which is nothing but a mapping from y to z, not x to z. X to z is the mapping f, and you consider f restricted to y, which is a mapping from y to z. Okay, is it continuous? F restricted to y from y to z is continuous. Actually, it is continuous. Actually, if f is continuous, then f restricted to y from y to z is also continuous. How can you prove this? Suppose we have a topological space x tau and another one z du. Okay, f is a mapping from x to z. Then you consider a subset y of x or a subspace of x. Then this function can be restricted to y. This is f restricted to y to z. Okay. If f is continuous, we will prove f restricted to y is also continuous. Okay. So how can you prove this? Again, inverse image of open set is open. So I take an open set here and we need to prove that f restricted to y inverse of that open set is also open in y. Okay. So let V be open in set. Open set in Z. Okay. We have to prove that f restricted to y inverse of V is opening not x, it is open in y. Y il ninna function thodangane, open in y. Okay. So this is we want. So what is actually f restricted to y, the whole inverse of V? You consider this set. Okay. Suppose I take an element, let x belongs to f restricted to y whole inverse of V. Which means f restricted to y of x belongs to V. If functioning out or no. Okay. Appo idinte inverse f restricted to y of x will be belongs to capital Vi maru. So what its meaning? Which implies it is nothing but x is an element belongs to capital Y. F restricted to y is a mapping from y to z. So if we apply the function f restricted to y on a point, that point must be belongs to y. Okay. So x belongs to y and f belongs to y and x belongs to f inverse of v. This is the meaning. X y il undu, f inde inverse image ilum undu. Adondana f restricted to y il ayathu. So this is the meaning. So which implies x belongs to y intersection f inverse of v. So whenever a point belongs to f restricted to y inverse of v, which means that that point is also belongs to y and f inverse of v. So which is implies and implied by actually. So we can see that f restricted to y whole inverse of v is nothing but y intersection f inverse of v. These two sets are actually equal, same. Therefore, in order to prove this, we have to prove this set is open. So we need only prove that y intersection f inverse of v is open. Okay. And we have assumed that f is a continuous function. F is continuous. So when f is continuous, if we consider any open set here, inverse image of that open set will be open in capital X. Okay. Since f is continuous and V is open in Z implies f inverse of V is open in capital X. Okay. Now what is capital Y? Capital Y is nothing but subspace of capital X. Okay. Then what is the form of open set in the subspace topology? A set is open in the subspace topology. It is of the form some y intersection G where G is open in X. Okay, y intersection G is open in X. Therefore, since f inverse of V is open in X, you can consider this as some G. Then, whenever we have a open set in capital X, then y intersection that open set will be open in Y with respect to the subspace topology. So, y intersection f inverse of V is open in Y since Y is a subspace of X. So it's the open sets are of the form y intersection G where G is open in X. Here instead of f inverse of V we can here f inverse of V is open in X, therefore y intersection f inverse of V will be open in Y. Okay. So what is this? This is nothing but f restricted to y whole inverse of V is open in Y. So what you get now? If we consider any open set in Z, any open set V in Z, F restricted to Y whole inverse of V is open in Y. F restricted to Y whole inverse of V is open in Y. Therefore, F restricted to Y is continuous. It is a mapping from Y to Z. Is continuous. So restriction of any continuous function is again continuous here. Okay. One more example. Suppose let X2 be a topological space. Be a topological space. Okay. And I consider a mapping I. Identity mapping. Okay. I is a mapping from X2 to X2. Be identity mapping. Okay. We are going to check the function identity map is continuous or not. Okay. So how can you check a function is continuous? Inverse image of open set is open. Okay. I take an open set here. Its inverse image under I must be opening this one. Okay. So let U be opening X. Rather, that means in the codomain. Okay. The codomain. Then you consider I inverse of U. What is I inverse of U? Since I is the identity map, I inverse of U is nothing but U. Okay. And what is U? U is open in X. Therefore, U will be belongs to tau. So what you get? I inverse of U is nothing but U, and U is also belongs to tau, means I inverse of U is open. Therefore, if you take any open set here, that will always open in here also, because I inverse is nothing but U. Okay. Therefore, I is continuous. I is continuous. Therefore, that means any identity map from X2 to itself is always continuous. Okay. If we consider the mapping identity mapping from X2 to X some U. Here the set is same but the topologies are different. X2 is a topological space and XU is the another topological space. Set wise they are equal but topological wise they are different. Okay. Is it continuous? If I is continuous, what will happen? If I is continuous, then inverse image of open set must be open for every open set. So I take then let V belongs to U. V belongs to U means V is open in X with respect to U. With respect to the topology U on X. Okay. We need to prove that I inverse of V must be open in X with respect to tau. What is I inverse of V? I inverse of V is nothing but, since I is the identity map, be identity. Okay, identity map. Since I is identity map, I inverse of V will be nothing but V. Okay, if I is continuous, I inverse of V must be belongs to tau. Clear? Since I is continuous, I inverse of V, that is equal to actually V, which must be belongs to tau. Since I is continuous. So what you get? Whenever I is continuous, then we take any open set in the codomain topological space, its inverse image will always belongs to tau. So V belongs to U means V belongs to tau. So whenever you take an element belongs to U, that element is also belongs to tau. So U will be contained in tau. So what is the meaning of this? Tau is stronger than U. So what can we conclude? Whenever X2 is a topological space and identity mapping is a mapping from X2 to itself, then clearly I will be continuous. If identity mapping is a mapping from X2 to XU, same set but the different topologies are varying, then if I is continuous, the tau must be stronger than U. That means topology on a domain must be stronger than topology on the codomain for a same set. Clear? For one more example, suppose f is a mapping from x to d to x to, where to d is discrete topology. To d is discrete topology, and to be any topology. Okay, so x to d is I write y. Okay, both are different spaces, x with discrete topology and y with any arbitrary topology, and f is a mapping from x to y. Okay, it may not be identity. Okay, x to y, x and y are any arbitrary sets. Okay, I am going to check the function is continuous or not. If the function is continuous, inverse image of open set must be open. That means for every v in tau, f inverse of v must be belongs to tau d. So I consider let v belongs to tau. V belongs to tau means v is open in y. You consider f inverse of v. Consider f inverse of v. What is f inverse of v? F inverse of v is nothing but actually, suppose this is x tau d, okay, whatever it is, this is y tau and f is mapping between them. I take v here, then f inverse of v will be here. This is f inverse of v. So f inverse of v is nothing but a subset of capital X. F inverse of v, comma, f inverse of v is nothing but a subset of capital X. Okay, inverse image is always subset of domain. And what is capital X? Capital X is a discrete topological space. X with a tau d denote discrete topology. So in a discrete topological space, you all know all subsets are open. Every subset is open. Here f inverse of v is a subset of capital X. Since the topology is discrete, f inverse of v must be open in capital X. Since X has discrete topology, comma, f inverse of v must be belongs to tau d. That is, f inverse of v is open in capital X. So for every open set v here, f inverse of v must be open in X. This is true for every set, not only for open sets, for any set. Therefore, I can say that this function f will be continuous. Therefore, f is continuous. That means, if we consider any function from a discrete space into any space, that will be obviously continuous. So, any function from a discrete space, discrete topological space into any space will be always continuous. Okay, clear? Now, what about the case of indiscrete topological space? So, let us consider a function. So, let f is a mapping from x tau to y tau I. So, where x tau is be any topological space, and y tau I be indiscrete space. That means y with the indiscrete topology. The open sets are phi, empty set phi and y itself. Okay. So whatever the function, is it continuous or not? Okay. For that, I need to consider some open set here. Its inverse image is open or not. Okay. So let v belongs to tau I. We are considering an open set in y. Open set in y means that must be belongs to tau I. We know that tau I is nothing but indiscrete topology. What is indiscrete topology? It has only open sets are empty set and full set. So V is of the form either empty set or V is of the form the whole set Y. So you consider what is F inverse of V. F inverse of V is either F inverse of empty set or F inverse of full set. So what is F inverse of empty set? F inverse of empty set is empty itself. And what is F inverse of Y? Since F is a mapping from X to Y, it is a mapping from X to Y, inverse image of the whole codomain is always the domain capital X. So F inverse of Y is nothing but phi or X. So F inverse of V is of the form either empty or capital X. Okay. What is X tau? X tau is a topological space. In a topological space, topology always consists empty set and full set. Therefore, F inverse of V will be open in capital X. F inverse of V is open in X. Why? Since phi and full set are always belongs to tau. Tau is a topology on capital X. So what you can say? If we consider any open set here, there is only two open sets, empty set and full set. Their inverse image is nothing but empty set and full set. Therefore, any function f can be any function. So, any function from an arbitrary topological space into an indiscrete topological space is always continuous. So, we can say that f is continuous. That is, any function from a topological space into indiscrete space will be continuous. Any function will be continuous into an, if it is a mapping from any space to indiscrete space. Okay.